All right, everybody, we'll go ahead and get started. And I want to begin with just some stuff, a little bit of a review on epoxides, which we mostly finished last time, but I wanted to review because it's a little complicated and because the ideas involved in it will come up again. Remember that we said that there are two different ways that you can open up an epoxide ring. One, I guess I wanted that to be a methyl group. One was under strong nucleophile conditions. What do we mean by strong nucleophile? Generally something that's negatively charged, conjugate acid with pKa greater than 0. As an example, we might choose deprotonated alkyne. When you use a strong nucleophile, the mechanism is very SN2-like, and so the major factor that dominates which of these two carbons gets attacked is sterics. So you will attack the less substituted carbon because it's easier to do that. I'm going to draw the alcohol product without drawing you the negatively charged intermediate. Here is the nucleophile. It comes in from behind and the oxygen leaves and then subsequently gets protonated to give you this product. We might say that this reaction was regioselective. By that we mean the reaction was selective for having the nucleophile end up attacking and then bonded to the less substituted carbon, and OH ends up on the more substituted carbon. I can't spell substituted carbon. Regioselectivity refers to connectivity. Regioisomers are isomers with different connectivity. We get the regioisomer where the alkyne is bonded to carbon 2 and not to carbon 1. And that's because the mechanism is very SN2-like. The nucleophile has to get in close to the alpha carbon before the leaving group leaves, and so sterics matter a lot. So that's one regioselectivity pattern. In contrast, if we take the same epoxide and open it up under acidic conditions, and I think the example we may have used was HBr, the first thing that happens is the oxygen gets protonated. That's lone pair electrons on the oxygen attacking the hydrogen bromine sigma star, and Br minus leaves. We get as an intermediate a protonated oxonium ion. And then Br minus acts as a nucleophile, and Br minus, we observe, tends to attack selectively the more substituted carbon to give you the following product, where Br, the nucleophile, is now on the more substituted carbon and OH is on the less substituted carbon. Again, this reaction is also regioselective, but in the opposite way. Br ends up on more substituted carbon. Now, we talked about where this change in regioselectivity comes from. A potential hypothesis was that maybe there's a carbocationic intermediate that looks like this, where Br can attack from above or below. But we can rule that out as an option because we only see the stereochemistry where Br and OH are on opposite sides of the molecule or trans to each other. So that means there can't really be a full carbocation intermediate. If there were, we'd expect to see some of the case where Br added from above. So the explanation for that is that there is no carbocation intermediate, Instead, if we could zoom in on the epoxide, I'll try to draw it in a slightly different way. Here are the two carbons in the six-membered ring, and here is the methyl group. As the reaction progresses, the oxygen here leans over, and it leans over away from the more substituted carbon. The bond isn't completely broken, but it's partially left. The bond is partially broken. As the oxygen begins to leave, the oxygen-carbon bond between oxygen and 1 gets longer, and there starts to be a buildup of partial positive charge on the more substituted carbon, and all of that happens before the nucleophile is even close. And call this the transition state. So, in the beginning, with this intermediate, oxygen had a choice. Which carbon is it going to partially leave from, 1 or 2? It's going to partially leave from the more substituted one because that can better tolerate the buildup of partial positive charge. It's not a full positive charge, but the same things that make a full positive charge more stable make a partial positive charge more stable. Go ahead.
What is the lumo here?
In what?
That row the nucleophile is attacking.
I'm sorry. What orbital is the nucleophile attacking here? The nucleophile would be attacking a carbon-oxygen sigma star. Yep. And the HOMO, of course, there would just be lone pair electrons. The protonated epoxide is the electrophile. All right. So that is why we attack at the more substituted carbon, and that is also why we don't attack from the top face, because the oxygen's still shielding that side, and it's still SN1, it's still SN2 in mechanism in the sense that we don't get a full carbocationic intermediate, but it is a more SN1-like SN2 reaction. And that seems kind of silly. The reason we talk about that in organic chemistry is because it helps us visualize sort of what the transition state is. When you recall, when we were learning about SN2 versus SN1, we thought about this occurring with two different things changing. One was that the nucleophile attacks, and the other was that the leaving group leaves. The mechanism that sort of went through the diagonal directly from starting material to products involved about the same amount of nucleophile leaving as attacking as leaving group leaving, and that was the SN2 reaction. In contrast, if we had the leaving group leave first, that would give us a carbocationic intermediate, and then the nucleophile comes in. That was our SN1 pathway. What we're saying for opening of epoxides under acidic conditions, imagine that this was the transition state where the leaving group is like 40% gone and the nucleophile is 40% attacked. Imagine just moving that transition state in the direction of leaving group leaves without changing where the nucleophile is. The new transition state would be here, and the new mechanism doesn't get to a carbocationic intermediate, but the transition state it goes through has a much larger percent of leaving group left, and therefore a much larger amount of partial positive charge on the carbon that the leaving group is leaving from. Okay, questions you want to ask about that? Yes?
Does the leaving group, does the nucleophile have to be attacking for the leaving group to start leaving in this reaction as well?
Does the nucleophile have to be attacking for the leaving group to leave? Well, it looks like the leaving group's allowed to leave more than the nucleophile attacks in, based on, if the reaction followed this orange trajectory, we'd say the leaving group leaves faster than the nucleophile comes in. Yeah, good. What else? Yeah?
I had a question about the first one. Is it the number one we did at the top?
Yeah.
Is it being protonated by the surrounding solvent?
Yeah, so where does the proton come from? And the answer is probably, if you were using this nucleophile is also a strong base, so you probably wouldn't want a solvent that could protonate anything at that stage because you just neutralize your base. But the negatively charged intermediate that would form, usually with these reactions, there's a workup step where you try to isolate the desired product and purify it. And one of those steps involves adding water buffered at some pH to the organic mixture and shaking it up. And then you can isolate, and that process will protonate everything that can be protonated at that particular pH. So probably that hydrogen, or the proton that we get, comes from water in some aqueous workup step. Sometimes your text will show that step explicitly in a mechanism. That makes it sound like it's rated something other than for children, but by that I mean actually showing it instead of implying it. Other times your text will just write proton transfer. Often it's not a separate step, really. It's just considered part of finishing up the reaction and moving on to the next phase. Okay, good. What else? All right. In the future, you're going to see another intermediate that's very similar to a protonated epoxide. It's called a Bromonium Ion intermediate, and regioselectivity of opening up a Bromonium ion will be very similar to that of opening up an epoxide. All right, so that does it for chapter 9. In chapter 10, we're going to shift, not in terms of really of what the reagents are, but we're going to shift in terms of what the organic starting material is, what the nucleophile is. If you think about it, through chapters 7, 8, and 9, the nucleophile has always been some kind of atom with high energy lone pairs on it, whether that's a nucleophile or a base. Today we're going to shift to the nucleophile being an alkene or an olefin. And sorry, I just had a Lord of the Rings moment. I'm imagining Samwise Gamgee saying, "Look, Mr. Frodo, olefins." And then there's also the lame Ochem joke, help, help, I'm dying. Womp, womp, wah, wah, wah. Anyway, olefins is nucleophiles. That means that the orbital we're going to be thinking about, the highest occupied molecular orbital, is going to be the carbon-carbon pi bond. So that's going to introduce a couple of complexities. Let's just imagine a cyclohexene like this with carbons 1 and 2. And actually, let's put a methyl group on carbon 1. When the pi bond acts as a nucleophile, issue number 1 is that the top and the bottom faces of the carbon-carbon pi orbital are the same, so that the carbon-carbon pi orbital can attack an electrophile above the pi bond or below the pi bond. You got two faces to attack from. So that will have some stereochemical implications in terms of whether the electrophile that gets attacked ends up above or below the ring. Or above or below where the pi bond used to be. Okay. The second issue is one of regioselectivity. And it is this: when the olefin attacks, you make a new sigma bond. But the carbon-carbon pi bond involved two different atoms, carbon 1 and carbon 2. So you have to think about which one gets the new sigma bond. All right, and you're going to make the new sigma bond between carbon and the electrophile, whatever it is, so that a positive charge ends up on the more substituted carbon, if there's a choice. And this rule, your text gives a name. It's called the Markovnikov Rule. And products that obey this pattern are called Markovnikov products. I don't care that you know or memorize that name. But the idea is when the pi bond attacks to make a new sigma bond between a carbon and an electrophile, you're going to put that bond on the less substituted carbon so that the more substituted carbon can have the positive charge. Because you're taking these two electrons now, and instead of sharing them evenly between 1 and 2, you're taking them away from either 1 or 2 and sharing them with the electrophile. And in this case, we would choose to put the bond between carbon and the electrophile on the less substituted carbon so that the more substituted carbon could have the positive charge. Final issue is one that you're already familiar with based on the SN1 reaction. Carbocations are planar and can be attacked from above or below. And that's most of what you need to know for the first couple of reactions in Chapter 10. And then the ones that we discuss after that will be unique in their ways of dealing with and working around some of these problems and issues. I think it's probably best just to illustrate these trends by showing you an example. And your text calls this example hydrohalogenation of alkenes or olefins. This is a reaction that we'll call an addition reaction for reasons you'll see in a minute, and it is basically a backwards elimination reaction. It's the opposite of an elimination reaction. I'm going to choose as our starting material a compound that will illustrate a lot of the stereo and regiochemical issues. I'm using the letter D here to represent deuterium. Deuterium is basically the exact same size as hydrogen. Its nucleus is just one mass unit heavier because of a neutron. But recall that the nucleus is only a really small part of an atom anyway. Most of the atom is taken up, most of the space in an atom is taken up by the electrons surrounding that atom. So deuterium is just like hydrogen, only we have chemical tools to tell the difference between them. And that will be useful in teasing out all of the stereochemical issues with this reaction. The olefins going to be our nucleophile, and therefore the HOMO is going to be the carbon-carbon pi orbital, which is both above the plane of the page and below the page. If we were to draw that here, it would look something like, oh, don't like that. Look something like this, where the different color represents different wave function sign on either face. The electrophile that we're going to use, let's choose HCl. It could be HBr. The electrophile, the relevant orbital in the electrophile is the hydrogen chlorine sigma star. The pi electrons will attack that sigma star at hydrogen so that chloride can be the one that leaves with its electrons. All right, so let's deal with the first issue noted above. I'm making a new carbon, we need to deal with all of the issues at once. I'm making a new carbon-hydrogen bond. We'll call this carbon 1 and carbon 2. Which carbon of my original alkene should get the hydrogen? 1 or 2? Okay, 2, so that the positive charge could be on carbon 1, because that's the more stable option. Excuse me. Now, the pi bond could have attacked either from the top face or the bottom face. If it attacked from the top face, the hydrogen would be coming out towards us, and the deuterium would now be back into the page. In contrast, if hydrogen were attacked from on the bottom face of our alkene, the hydrogen would be below the page and the deuterium would be above the page. All right? You get both of those stereochemical possibilities. This is a carbocation intermediate, and these two carbocations are enantiomers of each other, and they have to be formed in a 1-to-1 ratio. All right? Now, this is why I chose to put deuterium on carbon 2, because I wanted to show you that hydrogen could end up above or below, and if carbon 2 had just been bonded to a hydrogen, how would we know whether the hydrogen from our acid was added from above or below? Excuse me. All right, questions so far? All right, so at this stage, we've got a carbocation, and we have Cl minus, the leaving group from our acid. That's it for the new stuff. Frankly, from this point on, it's just SN1, right? It's a carbocation, and you have a nucleophile. The carbocation is the electrophile, and the relevant orbital there is the empty p orbital on carbon 1, and then the relevant orbital is lone pairs on the chlorine. So chlorine can attack from above or below either of those two enantiomers. And the enantiomers have identical chemical and physical properties, so they have to be attacked at the same rate. Okay? Let's draw the products that would come from that. From the enantiomer on our left, that's the one where deuterium is down and proton is up. We could end up with a molecule where chlorine was also up and methyl group was down. Or we could end up with a molecule where chlorine was down and methyl was up. Okay? Then from the other enantiomer, we could get another set of stereoisomers. In both of these, deuterium is up and hydrogen is down. Here, let's put chloro down and methyl up. And here, let's put chloro up and methyl down. And maybe let's call these enantiomers 1, or let's call these stereoisomers 1, 2, 3, and 4. Okay, we get 4 possible products because there's 2 different times where we can choose one of 2 different options. In the first step, we can attack the acid above or below. And then in the second step, the nucleophile can attack the carbocation from above or below. 2 options, 2 different choices, twice, that's 4 different outcomes. Notice we do not get any of the outcome where hydrogen ends up on carbon 1 and chloro ends up on carbon 2. We are totally regioselective for having the Cl end up on the more substituted carbon. but we get all of these stereochemical outcomes. So let's look at the relationships between these molecules. What's the relationship between 1 and 3? What do you see there in terms of the stereochemistry? An enantiomer, and you know that how? Because both configurations are opposite. Good. And how about 2 and 4? Oops. Looks like 2 and 4, and I'm just using color for stereochemical configuration. Looks like 2 and 4 should also be enantiomers. So the enantiomers have to be present in a 1-to-1 ratio. What's the relationship between this pair of enantiomers and this pair of enantiomers? Yeah, diastereomers. That's our word for any stereoisomer that's not an enantiomer. 3 is a diastereomer of 2 and of 4. 1 is a diastereomer of 2 and of 4. 1 and 3 are enantiomers, 2 and 4 are enantiomers of each other. We're going to introduce a way of talking about these two different diastereomers. It's going to be similar to the way we talk about alkenes. You remember alkene diastereomers, cis versus trans. We're going to have a related set of terms for these two pairs of diastereomers. Notice in the pair on the left, the hydrogen from our acid is on the same side of the double bond, of the original double bond, as the chloride. The thing that got attacked, hydrogen, is on the same side as the thing that did the attacking in the second step. Instead of using the word cis, which would make it easier, we've chosen to make it more complicated, and we'll use syn, which means same, as in synonym. And then on the right, you'll notice that the hydrogen ends up opposite, on opposite side of the molecule as the chloride nucleophile that came in the second step. And we're going to call this the anti-diastereomer. When using this term anti here, we're not using it in the same way as we use the term when talking about conformations and rotations around carbon-carbon sigma bonds. Anti to us used to mean, oh, this group A is anti to this group B. The dihedral angle between the two of them is 180. We're using the term anti more broadly to mean on opposite sides of the molecule. I don't know why we don't use trans versus cis here, but you could. So you've got the syn diastereomers and the anti-diastereomers. They can have different chemical and physical properties, and they don't have to form they don't have to be 1-to-1, but you get both options. There's no mechanistic reason why you can't get one or the other. So even though this reaction we'll say is regioselective for having chloro on carbon 1, that's true for all of our stereoisomers, the reaction is not stereoselective. It doesn't prefer one enantiomer over the other, and there's the possibility of getting both diastereomers. Now you could memorize that, but if you understand the mechanism, all of that just falls out of understanding the mechanism, right? You could, without knowing the outcome, if you understand HOMO, LUMO, and geometry of pi bonds and carbocations, you could come up with this outcome without a huge amount of trouble. I'll show you a shortcut, a couple of shortcuts for drawing products of these hydrohalogenation reactions. You may wonder, why did I have to draw 4 separate products? If you wanted to, you could represent all of this with a single drawing where you show where you draw the structure without dashes or wedges, and that communicates that all possible stereoisomers are present. Seems easier. But I wanted to actually show the dashes and wedges to highlight all of these stereochemical issues, because they're going to come up again and again in this chapter. All right, questions so far? Anything else? All right. So the text gives you a new reaction called hydration of alkenes, but this is not a surprise. It is basically hydrohalogenation, what we just did, but using H3O plus instead of HBr. You can also think of it as the reverse reaction of alcohol dehydration, which we just barely talked about in chapter 9. So again, here's your olefin starting material. I'm going to again choose to keep deuterium here to illustrate the various stereochemical issues. Question in the chat is, what would be the factors that would determine whether the syn or the anti-diastereomer might be preferred over the other? Certainly sterics could be. I could imagine that if both the methyl group and the deuterium were something really large, it could be favorable to have the anti-product so that those large things could be trans to each other. But I'm not going to ask you to predict that. There was a ton of questions and discussion in the first hour about whether the chair conformations would matter, and it's true that you could draw these 4 products and draw the 2 chairs that each of them could form, and then try to choose the most stable conformation for each diastereomer / enantiomer, and then see if you thought that one diastereomer was more stable than the other. But it turns out product stability only matters a lot when the reaction is in equilibrium, and in that case the most stable product wins. And once you have the chloride add to the carbocation, I don't think going back up the hill is very easy. So there are possibly issues that you could use to reason through this, but I'm not going to ask you to choose for this reaction whether you think the syn or the anti-diastereomers should dominate. Okay, others? All right, so you use a catalytic amount of H2SO4 in water. Water's your solvent here. It happens to be present in excess, and that actually helps us get to the desired products. As above with hydrohalogenation, you're going to get 2 diastereomeric pairs of enantiomers. By that I mean you're going to have one set of diastereomers where the hydrogen and the OH group are on the same side of the molecule, or at least on the same side of the original double bond. OH and proton were added to the same face of the pi bond. And then you're going to have the other pair of enantiomers where the OH and the hydrogen were added to different sides, different faces of the pi bond. This is where I get confused if I talk too much while I'm drawing, so I apologize. Now, again, if I wanted to, I could just represent all of that in the simpler drawing without dashes and wedges, but I wanted, doing that would gloss over the stereochemical issues. Like with hydrohalogenation, you have enantiomers where the hydrogen and then the thing you used as a nucleophile end up on the same side versus opposite sides. And as before, this pair of enantiomers would be the syn diastereomer, and this pair of enantiomers would be the anti-diastereomer. What about mechanism? Well, it's exactly the same as we saw previously. The first step involves pi electrons attack the sigma star between hydrogen and whatever this atom is. It could either, the acid could either be H3O plus, or it could be H2SO4. Either option is okay. You would get a carbocationic intermediate. Again, the first step is regioselective for having the positive charge on the more substituted carbon where it's more stable. Then water would come in and add to where the positive charge is from above or below. You would get an intermediate oxonium ion that looks like this. And then the conjugate base of your acid would remove the proton from the positively charged oxygen to give you these products, along with your regenerated acid, HA. And maybe I'll just draw it here. Each of these, by the way, is an equilibrium step. You'll notice that if we started at the end with the alcohol and used acid, we could go to the olefin. And if we started with the olefin and used an excess of water with our acid, we could get to the alcohol. You can use Le Chatelier's principle here to drive the reaction either forward or in reverse. If you want to start with the alcohol and end up with the olefin, you can simply set up a distillation apparatus that will remove your olefin from solution. Your olefin has a lower boiling point than the alcohol does. In contrast, if you want to end up with the alcohol, you simply add a lot of water, and that will favor formation of the alcohol. But mechanistically, this is not a different animal than hydrohalogenation. It's exactly the same mechanistic steps, and same stereochemical outcome. All right, other questions? Okay, with both of these, and this may come up in some problems in your text, anytime you have a carbocationic intermediate, beware of the possibility of carbocation rearrangements. And I don't have a specific example of that for you immediately, but you may encounter that in your text. So just be sure when you form your carbocationic intermediate, see whether there's any option to rearrange to a more stable carbocation. In this example, there's not. It's already a tertiary carbocation. Excuse me. All right. So the next reaction is going to be similar, but it's going to have a slightly different outcome. For the next reaction, we're going to see that we don't actually see both sets of diastereomers. We only see one. So I'm going to choose here just a simple cyclohexene. This reaction is called halogenation of alkenes or olefins. So the electrophile in this reaction is going to be a halogen like Br2 or Cl2. All right. As before, our olefin is going to be our nucleophile. and therefore the highest occupied molecular orbital that we're going to be thinking about is the carbon-carbon pi bond. Our electrophile is going to be Br2, and the most important orbital for the electrophile is the LUMO, which is the bromine-bromine sigma star. I want to take just a minute to contrast the electrophile we're using here versus the electrophiles that we've used above, like HBr or hydronium. The electrophile here does have a weak bond between bromine and bromine, but unlike HBr, the atom that's going to get attacked also has lone pairs on it. All right, and that's going to play a role. So I'll already show you what the products of this reaction are. Excuse me. We only see the anti-diastereomers. So I'm going to draw the two enantiomers that we get. We only see anti-diastereomers. We don't see any of the syn diastereomer. Okay, so what do you think that says mechanistically? Because it would be tempting to speculate by analogy to what we saw before that the pi electrons attack the sigma star and Br minus leaves. We make a new carbon-bromine bond with either carbon 1 or 2. They're identical, so it doesn't matter. And then the other gets the positive charge. But what's the problem with that? Carbocation could get attacked from above or below, right? So this intermediate does not explain the observed stereoselectivity. This reaction is stereoselective for the for the anti-diastereomer. So this is not a reasonable intermediate, because from this intermediate we would expect to see both syn and anti-products. So what's the alternative? Well, the alternative is kind of weird, but you can understand it. As we start, let's just suppose that we, because 1 and 2 are identical, it doesn't matter which, the pi electrons attack the bromine sigma star, and bromide leaves. And during that process, there should be a buildup of positive charge on the other carbon. So let's suppose that carbon 1 gets the new carbon-bromine sigma bond. As that process is happening, there's a buildup of partial positive charge on carbon 2. But before it can become a full positive charge, other lone pair electrons on Br minus snap it up and form a new carbon-carbon bond. Okay, and you could, I suppose you could think of the transition state as looking something like this. I'm going to use red for the dotted lines for things that are changing. The pi bond breaks. You start to form a new bond with Br, and at the same time, Br lone pairs come down and form a bond with the other carbon. That ended up being perhaps less informative than I thought it was going to be. And the product that you get is a three-membered ring intermediate where bromine is bonded to two things instead of one and has a positive charge. Bromine is bonded both to carbon 1 and carbon 2. We call this a bridged bromonium ion. You've seen things like this before. Remember when we talked about carbocation rearrangements and a hydrogen or a methyl group being shared evenly between two carbons? We called that a bridged carbonium ion. Same kind of language here, a bridged bromonium ion. Though we can't label electrons, you can imagine one of these bonds coming from the pi electrons of the olefin and the other bond coming from lone pairs on bromine. Almost as though this is sort of a mutual HOMO attacks LUMO kind of reaction. One of those is pi bond attacks sigma star, and then the other is lone pairs attack incipient or nascent p orbital on the carbon that would otherwise have a positive charge. So this bromonium ion looks and acts a lot like an epoxide, only it's not quite as strained because the carbon-bromine bonds are pretty long, because bromine is large. Okay, questions so far? Yeah?
Could you predict that this process would happen without experimental data?
Could we predict that this process would happen without experimental data? Well, hindsight's 2020. I saw a bumper sticker I think it was supposed to be related to like the 2020 election campaign, but it said something, hindsight in 2020, making yesterday clearer tomorrow. Okay, whatever. Sorry. Anyway, I'm not sure. The pattern of the kinds of molecules that can do this are heteroatoms that are involved in weak bonds and that also have lone pairs on them. We're going to see in chapter 12, there's going to be a reagent called MCPBA that looks like this. And it's going to make epoxides and do basically the same thing. You have a weak bond that a nucleophile can attack, the oxygen sigma star, and at the same time you have lone pairs on the oxygen that can go back and attack the nucleophile. So from that perspective, yeah, there's a pattern that you can learn from and use, but no, I'm not sure we would have predicted it in advance. Yeah.
This might be kind of just like a silly question, so if it is, you don't have to answer. But how do we know like it wouldn't just be like a whole concerted, like one-step reaction where the two PRs like both attach at the same time? Like, is that even possible? Or
Okay. So, Staten, I think you're proposing a transition state that looks something like this. Those carbon-hydrogen bonds are coming out at you. And I suppose you would need the BR to be like this, sort of spanning it from that direction. That looks okay. The only problem I see with it is it puts the sigma star orbital of the bromine not that close to the pi bond. I will tell you, though, that in a more complicated world, there is some evidence that for some molecules with pi bonds, I'm going to hate this, and this is why I don't do the alkynes chapter, because alkyne reactivity is complicated. But there's some evidence for some kind of ternary reaction like this, which also explains this, the trans selectivity. But I'm going to erase that, and we're going to just pretend like that doesn't exist. La, 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 not listening. So, okay, good. What else? Yeah.
How do we get from the bridge bromonium ion to the anti-diastereomer?
Great. How do we get from the bridge bromonium ion to the anti-diastereomer? Same way that we open the epoxide. Br left, and so in the second step, even though we don't have a carbocation, we do have Br minus. Just as we did with opening an epoxide, Br minus can attack from behind in sort of SN2 fashion. I'm worried about these arrows. And that will give you this product. Of course, if the Br attacked carbon 1, we would get the other enantiomer. There's some stereochemical issues here that we can talk about next time, but notice that the bromonium ion is meso. Those two carbons are identical, and if we attack either one, we get these two enantiomers. Okay, that's a good place to stop. I will see you next time.